We've now looked at the development of mathematics in ancient Babylon, in ancient Egypt, also in the Greek world, in the Eastern Mediterranean, in India, and in China. And in this lecture, we're going to draw all of these different mathematical strands together in the Islamic world, what is usually referred to as Islamic mathematics. That does not mean specifically mathematics connected with the religion, but rather the mathematics that was encouraged by this entire Islamic culture in the Middle East. Some of the big ideas that we're going to look at are the creation of algebra, advances in number theory, and eventually we're going to come back to this Islamic period and look at Islamic art in a much later lecture. The Islamic period, of course, begins with the Prophet Muhammad. The Islamic calendar begins in 622 AD, when Muhammad flees Mecca to Medina. And I want to focus on the Abbasid Caliphate that began around 750 AD. A few years after the founding of this caliphate, the capital of the Islamic world was moved to Baghdad. And for the next several hundred years, Baghdad would be the cultural center of the Islamic world, and it would become a very important center for the development of science in general and mathematics specifically. The great Islamic leader who would sponsor a lot of this mathematical activity is Harun al-Rashid. He ruled from 786 until 809. And he decided that he wanted Baghdad to be this center of science and mathematics, and so he began collecting the great works and having them translated into Arabic. And we happen to know that the very first two works that he had translated were Euclid's Elements and Brahmagupta's astronomical work, the Brahmafutta Siddhanta. And so this shows immediately that Harun al-Rashid was drawing on all of the scientific accomplishments that were in existence, that were accessible at that time. Not just from Greece and the Hellenistic world, but also from India and South Asia, probably also to some extent from China, and then also drawing on the local tradition, that there had continued to be a strong astronomical, astrological, mathematical tradition in Mesopotamia. Baghdad is located in Mesopotamia, in what today is Iraq, and there still was a strong mathematical tradition that could be drawn on in this particular work. His successor, Abu Ja'far al-Mamun, who ruled from 813 to 833, would go a step beyond this, not just translating works into Arabic and building a great library, but also actually establishing the Bait al-Hikmah, or House of Wisdom. And so he set himself to do what Ptolemy I had done in Alexandria many centuries earlier, set up a center for scholarly work that was built around a library, would bring people together to look at what had been accomplished and create new insights. One of the first people who did this was Abu Ja'far al-Khwarizmi. We don't know the exact dates for al-Khwarizmi. He was probably born late in the 8th century and died sometime in the middle of the 9th century AD. And he wrote one of the most important books in the history of mathematics, the condensed book on the calculation of restoring and comparing, which sounds like a very strange title. This is actually considered to be the first book of algebra. And I've talked a bit about the development of the idea of algebra, how you can go back to ancient Babylon and find problems that today we think of as algebraic problems that were being done by the Babylonians, certainly problems that we would think of as algebraic problems being done by the Greek mathematicians. But algebra itself did not yet exist. And I talked about Diophantus and how he introduced the idea of a single letter as a variable, and the idea of an actual notation for a quadratic polynomial or a cubic polynomial. But algebra, as it is now considered, did not yet exist. What Al-Khwarizmi did was to consider the idea of an algebraic equation, and he's the person who comes up with this idea. The two words that he's using, restoring and comparing, the actual Arabic words are al-jabra and al-muqabala. And so this is restoring and comparing. He comes up with the idea of setting up an equation where you have two quantities that both involve your unknown. For example, you might have something like the unknown squared is equal to 10 times the unknown plus 22. So you've got an algebraic expression. And the problem then is to try to find a root or a place where this expression actually is equal, where you've got equality on both sides. And what Al-Khwarizmi does is he explains how to keep the equation in balance by adding the same amount to both sides, or subtracting the same amount, or dividing both sides by the same amount. And so this is the process of comparing and restoring. And his word al-jabra is the origin of our word algebra. It's simply a transliteration of the Arabic word. His name, incidentally, Al-Khwarizmi, is also the origin of our word algorithm, a word used in mathematics to mean a procedure that needs to be followed. And Al-Khwarizmi laid out this idea of the procedure needed to be followed in order to keep the equations in balance. Now, Al-Khwarizmi's algebra didn't look anything like our present algebra. He did not have the kind of algebraic notation that we use today. He did not use single letters to represent the unknowns. He would express those in terms of actual words, talking about the unknown and the square of the unknown. You didn't have an equal sign. That's something that would be invented in Western Europe in the 16th century. But you did have this idea of an algebraic equation. And that would be an important breakthrough moment that would really lead to a lot of the development of the idea of algebra. Al-Khwarizmi is also responsible for taking the idea of Hindu numerals. At this point, the Indians are using a full decimal system in the way that we use it today. They have the 10 digits, 0 through 9. They're using it in a place value system where you don't have to have a special symbol to denote what place you're in. You don't need tens, hundreds, thousands as symbols because you have the 0 as a placeholder. And it's Al-Khwarizmi who realizes how useful this representation of numbers is. And it's Al-Khwarizmi who is really responsible for spreading this idea of how to represent numbers across the Islamic world. Now, there are some problems that the Islamic algebraists and mathematicians still had to wrestle with. One of these was the question of whether or not to use negative numbers. And in fact, most of the Islamic mathematicians of this time refused to use negative numbers. In some respects, this goes back to Al-Khwarizmi. While he was willing to describe an algebraic equation, he still thought about its solution geometrically, in the same way the Babylonians did or the Greeks did. And if you're thinking about this algebraic equation geometrically, it doesn't make sense to talk about a negative length. And so negative numbers generally were avoided. Now that made life a lot harder when you were trying to describe how to solve a quadratic equation, so an equation that involved a quadratic polynomial, because if you've got something like x squared plus 10x is equal to 39, you can try to subtract the 39 from both sides, but you don't want to actually work with a negative 39. And more important than that, there are actually two solutions to this quadratic equation. There is 3, and the other solution is minus 13. And Al-Khwarizmi and the Islamic mathematicians of his time would only accept 3 as a legitimate solution to this particular quadratic equation. The next mathematician that I want to talk about is Thabit ibn Qurra. He also lived in Baghdad from about 836 AD to 901. He did important work in astronomy, geometry, mechanics, and he also worked in number theory. One of the interesting things that he did that I'd like to say a little bit about is his work on amicable numbers. Now, this is actually a problem that comes down to us from the Greek mathematicians. And what the Greek mathematicians would do is to take a number, look at its proper divisors, so the positive integers less than that number that divide evenly into, and add those up and see what number you get, and then repeat this process. So if I start with 12, its proper divisors are 1, 2, 3, 4, and 6. If I add those up, I get 16. If I now take the proper divisors of 16, those are 1, 2, 4, and 8. If I add those up, I get 15. If I now take the proper divisors of 15, they are 1, 3, and 5. If I add those up, I get 9. The proper divisors of 9 are 1 and 3. They add up to 4. The proper divisors of 4 are 1 and 2. They add up to 3. And 1 is the only proper divisor of 3. So this process started with 12, went up to 16, and eventually comes down to 1. Do we always come down to 1? No. And a simple example is the number 6. If I start with 6, and I add up its proper divisors 1, 2, and 3, I get back to 6. 6 is what the Greeks called a perfect number, because when you add up its proper divisors, you get back to the number itself. Now, another example of a perfect number is 28. Its proper divisors are 1, 2, 4, 7, and 14. Add those up, and I get 28 again. So one of the possibilities as you do this is you might come right back to the number that you started with. Something else can happen. If you start with the number 220 and add up its proper divisors, you get 284. If you take the number 284 and add up its proper divisors, you get 220. 220 turns into 284, 284 turns into 220. These are called, and they were called by the Greeks, amicable numbers, friendly numbers. The Greeks found this pair, 220 and 284. They also found another pair, 1184 and 1210. And it was Thabit ibn Qurra who went on and found the next pair, 17,296 and 18,416. That knowledge eventually would be lost to Western mathematicians. It would not be known to the people working in Europe centuries later. And in the 18th century, the great mathematician Leonhard Euler would re-find precisely this pair of amicable numbers that Thabit ibn Qurra had found and be very excited and quite pleased that he had been able to find this result that had in fact been found many hundreds of years earlier. The next mathematician I want to talk about is Abul Hasan al-Uqladisi. Again, we don't know exactly the years he lived, but he was sometime in the middle of the 10th century. We know that he lived in Damascus. And one of the books that he is best known for is the Kitab al-Fusal fi al-Hisab al-Hindi, or the Book of Chapters on Hindu Arithmetic. As I said, al-Khwarizmi was important for urging the adoption of the Hindu method of representing numbers. This particular book really shows how effectively this Hindu decimal system can be used in order to do calculations. And one of the things that we find in this book by al-Uqladisi is the first use outside of China of decimals to represent fractions. And there is a page from one of his books that I'm showing up now. If you go down to the 10th line of this page from al-Uqladisi's book, the stretches of Arabic writing that have a line over them represent numbers. And if you go down on this 10th line, you will see a number that has a hash mark over one of the digits. And that hash mark is used to mark where the units are. Now, of course, instead of reading the number from left to right, you read the number from right to left in the Arabic fashion. And so you read it from right to left. When you get to the hash mark, that designates that you're now in the ones place, and the next digit is representing tenths, and the digit after that is now representing hundredths. And it's Al-Uqladisi who manages to convince the Islamic mathematicians to begin using this idea of decimal fractions. I would love to know whether they borrowed this idea from the Chinese, who had been using it for many hundreds of years up until now, or if this was an independent discovery of this powerful way of representing fractions. The next mathematician I want to talk about is Abu Bakr al-Karaji. Again, we don't have exact dates on him, but he was born sometime late in the 10th century and died sometime in the early 11th century, perhaps around 1030. He also would live in Baghdad. The book that he is best known for is Al-Fakhri, which means the marvelous. And one of the things that he does that will be extremely important as we look at the further development of mathematics is this idea of taking the unknown and raising it to an arbitrary power. So you can take the unknown and you can square it or cube it or take it to the 37th power. You can also take it to a power that is a negative number. So he talked about how to represent the reciprocal of the unknown by using a negative power. So x to the minus 2 is the same as 1 over x squared. So he was working with positive exponents, negative exponents, and he pointed out how useful these exponents are because of the way that they combine. If I have x raised to the 3rd power and I multiply that by x raised to the 5th power, I can combine those just by adding the exponents. That's going to give me x raised to the 8th power. And he states the general rule that the unknown raised to the mth power times the unknown raised to the nth power is equal to that unknown raised to the m plus nth power. And the same thing is happening if you take x to the m divided by x to the n. That's going to be x to the m minus n. This is also the mathematician who would be credited by Al-Samaval, a 12th century Islamic mathematician, with being the first Islamic mathematician to discover Pascal's triangle. Now, unfortunately, we do not have any independent evidence that this really was the first Islamic mathematician to discover Pascal's triangle. If he was, he lived before Jiaxian, and so that suggests that perhaps Pascal's triangle came up first in the Islamic world. We're uncertain about this. Whatever happened is that amazingly in the 11th century, Pascal's triangle appears both in China and also in the Islamic world. And it would be wonderful to know if there was some kind of communication between them. Did one of them discover Pascal's triangle and then share the information with the other? Or was it just that both of them were working with this problem of arbitrary polynomials? And inevitably, as you begin to work with polynomials of arbitrary degree, you begin to come across Pascal's triangle, this idea of these powers of the binomial 1 plus x. And what we find in the Islamic world, just as there was in China, Pascal's triangle comes up as a method for finding roots of arbitrary polynomials. One of the most interesting mathematicians from the Islamic world was Abu Ali al-Haytham, born in Basra sometime around 965 AD. Al-Haytham was an engineer, and he made his reputation in Basra in southern Iraq early in his career. And then sometime around the year 1000, he was enticed to come to Cairo. Now, Cairo had been founded as the capital of the Fatimid Caliphate in 969. And one of the first things that was constructed in this brand new city of Cairo was a mosque, the Al-Azhar Mosque. And one of the first things that was done at the Al-Azhar Mosque was to create a school of learning. And this would continue to be a continuously operating center of learning ever since its founding in 975. In 996, Al-Haytham would become the caliph. He was only 11 years old at the time, and he would become known as someone who was quite cruel, quite eccentric, but he also was someone who was very interested in developing the sciences, and so he went out and found good scientists to bring into Cairo to help build the scientific community in this city. And Al-Haytham was one of the people that he brought in. Now, Al-Haytham was initially brought in to be an engineer, and actually the job that he was given was to travel south along the Nile River and find a place to construct a dam so that they could control the flow of the Nile. Al-Haytham traveled upriver and discovered that the job was simply well beyond the engineering capabilities of that time. He never built the dam. And when he came back to Cairo, he became rather afraid of the caliph because of his tendency both to be capricious and also cruel. And so Al-Haytham feigned madness. He disappeared into his own house. But while he was doing that, he was developing his mathematics and his science. And one of the areas that he really worked on very extensively is optics. So understanding how mirrors operate, and especially mirrors of different shapes, spherical mirrors, scientific mirrors. He would actually publish 92 scientific works, many of which dealt with optics, many of which dealt with mathematics, other scientific topics. 55 of Al-Haytham's books still survive today. Among the mathematics that he did was to work with the Chinese remainder theorem. Again, it's not clear if he was drawing on the Chinese tradition or if he came up with it independently. He came up with something that would later be known as Wilson's theorem, and that's the observation that if you have a prime number like 7, and you take the product of all of the integers that are less than that prime, so you take the product of the integers from 1 up to 6, and then add 1 more to it, that number will always be divisible by that prime. So the product of the integers from 1 to 6 plus 1 is 721, and that's divisible by 7. 11 is a prime. The product of the integers 1 through 10 plus 1 gives you 3,628,801, and that number is exactly divisible by 11. Al-Haytham didn't just observe this, he actually was able to prove this particular result. He was using polynomials in their fully general sense, and he was able to take Archimedes' ideas for finding areas, finding volumes, using the method of exhaustion. And he really pushed these much further than anybody had been able to do before. One of the volume problems that Archimedes was able to solve is the problem of finding the volume of a paraboloid. So we consider a parabola, and we take the line of symmetry, and we then rotate this parabola around the line of symmetry, and that gives you a kind of bullet shape. And that bullet shape is what is called a paraboloid, and Archimedes had figured out how to find the volume of a paraboloid. The problem that Al-Haytham tackled was to take this same parabola and rotate it a different way. What he did was he just took half of the parabola, say we take the top half of the parabola, and then we take a vertical line that chops this arc of the parabola at some point, and we rotate that piece of the arc around the vertical line. What we get is a solid that looks very, very different from the paraboloid of Archimedes because it's a solid that comes to a point. And you can actually see this solid of Al-Haytham that is in the domes of many of the mosques. This would become a common motif for Islamic mosque art. And what Al-Haytham does is to work out the volume of this particular solid of revolution obtained by rotating a parabola, but in a very different way from the way in which Archimedes did it. He does this by slicing his particular solid of revolution in much the same way that Archimedes does. But the problem's much harder. What Archimedes was able to show is that in order to find the volume of the paraboloid, you really only need to be able to find the area of a triangle. And you can reduce one problem to the other problem. For Al-Haytham, trying to find the volume of his solid of revolution, what he needed to be able to do was to find a formula for adding up the fourth powers of all of the integers from 1 up to n. 1 to the fourth plus 2 to the fourth plus 3 to the fourth, all the way up to n to the fourth. Now, the sum of the integers from 1 to n, that particular formula had been known since far antiquity. In fact, that's so old we have no idea where it first came from. It was certainly known to the earliest Greek mathematicians. It was known to the earliest Indian mathematicians of whom we have any record. That formula was well known. If you consider the sum of the squares, 1 squared plus 2 squared plus 3 squared up to n squared, that particular formula, it gives you a cubic polynomial in n, that also was known to Greek mathematicians. The sum of cubes, 1 cubed plus 2 cubed plus 3 cubed up to n cubed, that involves a fourth degree polynomial. We don't know when that was first discovered. It might have been discovered by the Greek mathematicians. It was certainly known to the Indian mathematicians by the middle of the first millennium AD. But Al-Haytham needs to go beyond this. He needs to add up fourth powers. And one of the things that he does is to find the fifth degree polynomial that gives you the sum of the fourth powers. And beyond that, he comes up with a general procedure that can be used to find the sum of fifth powers or sixth powers or any powers beyond that. I want to talk just briefly about a few of the other important mathematicians who would appear in the Islamic world after Al-Haytham. The first of these is Ibn Yahya al-Samaval, lived sometime in the middle of the 12th century in Baghdad. This was well after Baghdad's heyday. Baghdad was no longer the place to go for mathematical and scientific work. But nevertheless, al-Samaval did become a very important mathematician. He was actually trained as a medical doctor. He was Jewish, and he's one of the first Jewish mathematicians that we know of from history. Eventually, in middle age, he did convert to Islam. He worked with polynomials, and he really understood the full power of polynomials. And he is someone who is able to explain how to take a polynomial and divide it by another polynomial. It's something that today we call synthetic division. And just as if you take one number and divide it by another, you begin to get a decimal expansion that may keep on forever. There may be no end to the decimal expansion. Say if you're going to take a number like 3 and divide it by 17, the decimal expansion repeats, but it never ends. So Al-Samaval realized that if you take one polynomial and divide it by another, what you're going to get are negative powers of the unknown appearing. So you'll get a term in x to the minus 1 and a term in x to the minus 2. And he realized that these negative powers could well continue forever. He is also someone who did a lot of work with Pascal's triangle. It turns out that there's a very clever formula for finding the sum of second powers, third powers, fourth powers, whatever power you want to fix on. You can find a formula for the sum of those powers using Pascal's triangle, using the numbers in Pascal's triangle. And Al-Samaval, we believe, was the first person to discover this. One more mathematician I want to mention just very briefly is Omar al-Khayyami. 1048 to 1131, lived in Isfahan. The very famous Persian poet. What many people don't realize is that in addition to being a poet, he also was a very accomplished mathematician. And he was particularly interested in the problem of finding the exact value of the roots of a cubic polynomial. And he made progress on this. He was not able to finally solve this problem. It would actually take about 400 years before this problem would be solved. And it would be solved in Western Europe by Italian algebraists. This would be the first mathematical accomplishment of the European world, the Western European world, and that will be the topic of my next lecture.